Good morning, guys. Anjani Kumar here, dealing power system 2 for third year electrical students. In a last session, we discussed about proximity effect, right? So we are discussing various factors that affect the transmission system while traveling the power, while transferring the power from sending end to the receiving end. So what are the factors? You know the factors are skin effect, proximity effect, Ferranti effect, and corona. So these four factors are predominant role while transferring the power from sending end to the receiving end. So in that we discussed about a skin effect. So what is a skin effect? Skin effect states that the current near the surface of the conductor having a maximum current, and the center of the conductor the current is a minimum current. So these non-uniform current present in a conductor will create some problems, right? So this phenomena, this effect, we can call it as a skin effect, right? We discussed about various factors that affects the skin effect, right? We discussed in detail about the skin effect, right? After that, we discussed about proximity effect. So proximity effect states that, I just want to explain briefly the last session, right? So what is a proximity effect? Proximity effect states that if it is a conductor, so if you take the cross section of the conductor, right, conductor divided into two parts, the top of the conductor, either bottom of the conductor will carry the current only. Either one side of the conductor will carry the current, other side we don't have a current. So that means this phenomena, this effect, we can call it as a skin effect. I hope it's clear, right? One conductor is there, so you are transferring the power through a conductor, means throughout the conductor will carry the current, right? So but it's not so only either top or a bottom portion of the conductor is carrying the current, right? Other side we are not carrying the current, right? So it can be explained in two ways, right? If the two conductors, two parallel conductors which is carrying the same current, so when two conductors carrying the same current, that means top side of the conductors, so in this way the current will flow, and the bottom side there is no current. Here the top side there is no current. Here the flux linkages is a maximum, right? We discussed in detail, right? And the second thing, when two conductors that are carrying current in different directions, right? So one conductor carries in this direction, you'll get the current only on the here the bottom place, here the top place. Here we don't have a current, here we don't have a current. So that means only one portion, either top or a bottom, the conductor carries the current. Remaining part is a non-carrying current part, right? So this phenomena we can call it as a proximity effect. So we discussed in detail about what are the factors that are affecting which need diagrams, right? After that we discussed about how to minimize the proximity effect, right? In order to minimize the proximity effect, the distance between the conductors too large. So we can vary the frequency, we can vary the voltage, we can maintain the proximity effect. But you are giving a AC supply means increasing or decreasing of frequency, which is not possible because the frequencies are fixed in a AC systems, right? So we have another target is voltage. We can vary the voltage, you can withstand that, we can vary the voltage right above or rated voltage, below the rated voltage with the help of regulators, right? So that means it's very difficult to avoid these type of effect in a transmission system. All right, now we are moving to another concept, another factor, so that we can call it as a Ferranti effect. Somewhat very, very important concept. Try to understand, right? So this is also one of the important effect that we need to consider while transferring the power from sending end to the receiving end. Alright. So in this we will discuss what is Ferranti effect. What is Ferranti effect? How it will happen? And how we can reduce this one. Reduce this one. Right, these are the things that we need to know, right? So this is we can also call as a charging effect, right? Charging current effect. Why we can call it as a charging current effect? We discussed, right? Charging current effect in a transmission system. Transmission lines. Right, Ferranti effect we can also call as a charging current effect. Now, first before going to the phenomena, we just discuss how it will happen. Then we will discuss. Then you will develop your phenomena statement. Right. Right. So we have a transmission system. Right. Correct. So this we can call it as a sending end. This we can call it as a receiving end. This is a transmission line. Right? So it is nothing but a conductor. Right? You know that if sending end voltage, if it is a 33 kV, so whatever the voltage so that you are sending end is a 33 kV. So how much voltage you get? How much you will get? So you will get 33 kV? Definitely not. Some sort of voltage reduction due to the losses in a wire conductor or a losses in a conductor. The conductor which is having some resistance now, due to that resistance copper losses will be developed. So due to this copper losses, the losses in voltage will be placed. So how much voltage you will get? 32.33 kV odd, right? So this is you know, right? This is a system scenario. So while transferring the power from sending end to receiving end receiving end, you won't get actual amount how much voltage that you are sending. So due to the losses, the output voltage will be reduces. But the scientist called Ferranti in 1890, scientist called Ferranti in 1890 says that in some other conditions, whatever the receiving end voltage which is greater than the sending end voltage, we think that it is not possible, right? But it's fact, right? Definitely the receiving end voltage what we are getting which is greater than the sending end voltage under some conditions, right? What are that condition, right? Right. So Ferranti states that under some conditions the receiving end voltage which is greater than the sending end voltage, right? So this effect we can call it as a Ferranti effect. So this effect called Ferranti effect. Right? So this is called sending end voltage, This is called receiving end voltage, right? So it's the statement receiving end voltage which is greater than the sending end voltage, right? So this scenario we can call it as a Ferranti effect. I hope it's clear, right? Ferranti effect states that under some conditions, so there will be a receiving end voltage which is greater than the sending end voltage. So this phenomena, this effect, we can call it as a Ferranti effect. Under which conditions, that we need to know. The first one is no load condition. If the receiving end, we don't have any load, in that condition definitely the receiving end voltage which is greater than the sending end voltage. No load condition, lightly loaded condition, and the third one is open circuited condition. Right? So these are the conditions. Under these conditions, so definitely your receiving end voltage which is greater than the sending end voltage. So this phenomena we can call it as a Ferranti effect. I hope it's clear. And what type of conditions means? The load which is, in receiving end you don't have any load, that means no load condition. If the receiving end open circuited condition and some small amount of load will be inserted, right, definitely you will get the receiving end voltage which is greater than the sending end voltage, right? This is a statement. I hope it's clear. Now we'll discuss about some important points. This is for your end exams or for gate exams or for IES exams, right? Right. The first point, you know what is Ferranti effect? A receiving end voltage greater than the sending end voltage. So VR is nothing but a receiving end voltage. VS is nothing but sending end voltage. Alright. And second point. So when a circuit having inductance and capacitance only will create this effect. What are the transmission line parameters for the cause of Ferranti effect means? This is very, very important question. This is also important in for your gate, IES and Polytechnic level exams, sub-engineers level exams. These type of statements are very, very important. Alright, so what is the first statement? The Ferranti effect says that VR greater than VS. So whatever the receiving end which is greater than the sending end. And when the Ferranti effects happen means when the circuit which is consisting of inductance and capacitance present in the system only, we will consider these type of effects in the system, right? So that means, so what type of transmission lines having inductance capacitance? Only medium and very, very important high transmission line. So only we will consider these type of Ferranti effect in medium and long transmission lines. High or long transmission line. So if you take a short transmission line, we don't have an effect of capacitance existence. So only inductance will be present in the system. Only resistive and inductance that are connected in series elements that are present in the system. We don't have any capacitance element. So that's why we need to neglect these type of Ferranti effect, because how the charging current will discuss, right? So in a short transmission line, so we don't have these type of Ferranti effect. So we don't have Ferranti effect in short transmission line. Right? So this is very important statement. Short transmission line, medium and long transmission line, L and C. Right? And another one, so on what conditions? So they will ask, on what conditions this receiving end voltage which is greater than the sending end voltage? You will know condition, no load condition, right? Open circuit condition, or it's lightly loaded conditions. We won't take the lightly loaded, but we need to write, right? Right. So these are the important points need to know when we want to discuss about the Ferranti effect. So these are the exam point of view. These are the notes we need to remember. Right? I hope it's clear. Alright. So now we are going to solve. So under open circuit condition, either whatever the condition you will take, so you have to prove that receiving end voltage which is greater than the sending end voltage. Right? I just want to take open circuit condition for a medium transmission line, either nominal pi method or a nominal T method, whatever it may be, and condenser method, whatever it may be. We just consider the capacitance existence. Right? So I just want to prove that the receiving end voltage which is greater than the sending end voltage, and it can be proved by mathematically and phasor diagram approach also. Right? So better to understand. Right? I hope it's clear. Right? Whenever the receiving end voltage which is greater than the sending end voltage, that phenomena we can call it as a Ferranti effect. So what is the main parameters to develop this type of concept means the inductance and capacitance present in a transmission system will create this Ferranti effect. So that's why these type of effects we will consider in the long transmission line or a medium transmission line. So we don't have this much effect in a short transmission line. Why? Because in a short transmission line we don't have a capacitance concept. Alright? That's it. Now I just want to derive how my sending end voltage which is greater than the receiving end voltage which is greater than the sending end voltage. Right? I just want to prove mathematical approach first. Right? So mathematical approach. Clear. I'm taking a medium transmission line which is having one capacitor, right? We just go for two capacitors, nominal pi method, nominal T method, whatever it may be. I just want to go for one capacitance that is existing at the receiving end side, right? Right? So only one capacitance that I am considering for your clear understand, right? So this we can call it as a sending end voltage. So this we can call it as a receiving end voltage, because this is an open circuit. That condition is nothing but the condition is open circuit. My load is an open circuit. So in that situation, we need to prove that your receiving end voltage which is greater than the sending end voltage, right? If you prove that, definitely the statement is correct. Otherwise, we can make it as a wrong statement, right? This we can call it as a XL. This we can call it as XC. This we can call it as a IC. This we can call it as sending end current. So this we can call it as a receiving end current. So I will write it. So what are the things, right? So Vs is nothing but sending end voltage. Vr is nothing but receiving end voltage. Is sending end current. IR receiving end current. Right? IC is my charging current. Right? So XL and XC is the parameters, transmission line parameters. Right? So now we'll start. So we know that the load is open circuited. Na? Here you will see your load is a open circuited. Open circuit means whatever the current IR is equal to 0. Na? There is no open. Open means there is so we don't have a current from this side to that side, right? Because it's a open circuited. What about IR? IR is equal to 0. Right? IR is equal to 0. If IR is equal to 0, whatever IS which is equal to my IC, na? I hope it's clear, right? So IS is equal to IR plus IC, okay na? So whatever the KCL you applied here, IS is equal to IR plus IC, but IR is equal to 0. We can make it as IS is equal to IC, na? That's another statement. These two things are enough. Now you just apply a loop equation here. The current in this direction. So this is a plus and this is a minus. Now you apply a loop. So how the loop will be? Current will flow from minus to plus. It will take it as a minus Vs. Minus Vs plus. What is the drop here? Is into voltage into current. Na? Is into XL, right? Plus. What is the voltage? I into R. Na? Plus. Is into XL. And what about the voltage here? Plus. IC into XC is equal to 0. Right? This is the loop equation, right? So from this you will state that Vs is equal to Is XL plus IC XC. Right? I hope it's clear. So from this Is into, you are considering the length of the transmission line is a L, small l. So we will consider here the length of the transmission line is small l. So what about the inductance is L into L? What about the capacitance C into L? So you need to remind this one. Now I am taking the length of the transmission line is L. So what about the parameters? If it is the inductance can be multiplied by the length of the transmission line. If the capacitance also multiplied by the length of the transmission line. Alright. Now what is XL here? Omega L. So what is L? L is nothing but L into L. I hope it's clear. So in place of L you have to consider L into length. Throughout the length, how much length the inductance it is. For a L length the inductance is L. Similarly IC into 1 by X is nothing but 1 by omega C, na? Omega C into L. I hope it's clear. In place of C you will put C into L because you are considering L length. Right? So from that you will write. So what IC? Is is equal to IC, na? So you can make IC is nothing but Is, na? Right? So from this Is common. Omega L into L plus 1 by omega C L. Right? So from this, what is Vs? Vs, so I'll write it here. Right? So you got the equation as Vs is equal to Is into omega L plus 1 by omega CL. Right? So what is the value of IS? Bs by omega LL plus 1 by omega CL. You got the IS value. So ultimately you have to find, you have to show that VR greater than Vs. So in that you calculate the value of IS. You know that. So what is the capacitance value? The capacitance which exists between the metal and the earth, or between the pole and the conductor. Right? So for suppose if this is a transmission line tower na, so right, you are placing one insulator here na, string insulator, right? So the capacitance existence, for suppose this is a transmission line, you will place a string insulator here. So the capacitance existence between the tower and the metal, so it should be very less. Small amount of capacitance will created here, and it will create large amount of effect. Right? So whatever the capacitance that existence between the conductor and the tower and the metallic frame, we can call it as a shunt capacitance that we discussed in detail in a string efficiency concept, right? So that affects the capacitance value will be very less. If the capacitance value very less means throughout this value will be very high now, right? So if this value is high when compared to this value, we have to neglect this one now. Right? I hope it's clear. So whatever the capacitance that exists between the tower and the metallic frame, insulator or a metallic frame, that capacitance is very less. That capacitance is very less means this concept, this term, it will be very high now. Right? When compared to this term. So we need to neglect this term now. So then what is the equation? Is is equal to Vs by 1 by omega CL. Okay, so how you can write down Vs omega CL. So ultimately the equation for Is is equal to Vs into omega CL. Right, now you have to calculate the value of VR. See, so what is a VR? So this is an open circuit now. So whatever the voltage applied, voltage here, which is the voltage across this capacitance now, because in a parallel voltage is constant now. What this is open circuit, how much voltage here, that much voltage that appear across the capacitance now. So whatever the voltage across the capacitance, which is my receiving end voltage now. I hope it's clear, right? What is my receiving end voltage here? Now, what is the receiving end voltage? So this we can call it as a VR. Right? Any doubts? Nothing is there, right? Now you said what is the value of VR? Just apply the loop, you will get that. Right? Now apply the loop. I'll write it here. So if you have any doubts, so the current is 0 here. So this we can call it as a Vs. So this we can call it as Is XL. This we can call it as IC XC. So whatever the voltage here, VR. Now you will calculate the equation for VR. Again apply the loop. This is a current loop. Apply the loop. You will get minus Vs plus Is XL plus VR is equal to 0 now. Nothing is there. Minus Vs plus Is XL plus whatever the voltage here, VR na, VR is equal to 0. So from this you will write it that VR is equal to Vs plus Is XL. Right? So I will write it here. So VR is equal to Vs plus Is XL. Alright. So what is the Vs? What is the Is value? You know the value of Is. Is is equal to VSWCL. VSWCL. Into XL is there na? XL means omega L into L. So if you common Vs 1 plus omega square CL L square. So from here you will see whatever my receiving end voltage which is greater than Vs plus something na, so that we can call it as a receiving end voltage VR which is greater than the Vs. So VR is equal to Vs plus something value, right? So that means VR value will be greater than the Vs value. Your statement is true now. Whatever the Ferranti said, that that statement is absolutely perfect. I hope it's clear. Nothing is there. Just KVL applied, right? So for a mathematical representation, that we did all these things, right? And here you will see the receiving end voltage, which is also depends on the length of the conductor. You will see. So receiving end voltage, on what condition your receiving end voltage which is greater than the sending end voltage, it depends on the length. If it is a medium transmission line, if it is a long transmission line, definitely you need to consider VR greater than Vs. That means here you see, if the length of the transmission line square times the receiving end voltage, if length is 2 meters. So what about the Ferranti effect? What is our receiving end voltage? It is 4 times. Right? Square times will be increases. If length increases, your voltage increases 4 times. So that is the length will increases, your Ferranti effect is increases. That means if you are receiving end voltage which is greater than the sending end voltage. This is one of the important, right? Square times. Right, this is the whole information regarding mathematical approach of this Ferranti effect. Now we'll discuss about phasor representation. Right, so I just want to briefly explain the phasor diagram. That is not that much important, right? I just want to draw the figure once. Right, so this is Vs, this is Is, this is XL, this is XC, this is IC, this is IR, this is PR. Right, so in order to draw the phasor diagram, you just have one reference vector. So what is that reference vector that you are choosing? Your reference vector is a VR. You can take it as Vs also. Right, I am take it as VR is my reference value. Right, now what is the VR which is equal to the capacitance current now? So whatever the current, whatever the voltage across a capacitor, which will be equal to the receiving end voltage now. Right, so that means what about the current? Is the capacitance now? Current will be leads by an angle 90 degrees. Right, so your current leads by an angle 90 degrees, right? So this we can call it as a capacitance, right? IC, right? So VR IC, because VR is across the capacitance. So what about the current which is a lead by an angle 90 degrees, right? So from this, what is VR here? Just apply. VR is nothing but, so there will be some resistance will be added now, IC into XR plus IS into XL now. See, we'll see here. So what is my VR? Vs plus ISXL plus ICXC. Alright, so what about the IC will be here. So IC or is considered IC into R. Similarly, you will exist here. So what about XL condition? XS will be J times, right? So from the perpendicular, ICXL, right? So if you combine ISXL plus ICR, so we can call it as a VS. So this we can call it as a VS. So from the representation, you will see this is the value of VS and this is a term of VR. This is a VR and this is a VS. So VR greater than VS. Right? So this is a phasor diagrammatical approach. So whatever the VR is nothing but here you will consider R value, right? So only not the inductor, the resistance also you can include, right? So what is a VS? What is a VS? VS is nothing but IS R plus IS XL. Whatever IS is equal to IC na, IC into R. So this is a statement of IC into R which is parallel to the current, and IC into XL. So IS is nothing but IC na, IC into XL. Nothing is there. You just consider this is a VR. Right? So you need to neglect IC, XC and all the components, right? So what you have to take the reference vector is VR and the current is IC, right? How you can calculate the VR? VS plus IS or plus IS XL. Any doubt? The statement is VS plus ISR plus ISXL is equal to VR na, right? I hope it's clear, right? So VS plus IS into R plus JXL na is equal to VR na. So IS is nothing but IC na, we can call it as IC na, R plus JXL is equal to VR. So whatever the IC term which is having a resistance and inductance value, right? For this you have to take the resistance value which is same portion. The current in a resistance, current is analogous, right? How the current flows in a resistance, all the parameters will be analogous, right? IC is same manner, right? IC into R. For inductance, J times, that is a perpendicular. J is nothing but 90 degrees na, minus 90 degrees na. So that's why this is a perpendicular. So whatever the VS, add this one. So this we can call it as a VS, right? VS plus ICXL plus that we can call it as a VR. So this is a phasor diagrammatical representation. So from this you will see whatever the content of VR which is greater than the VS value. So this is the statement of Ferranti effect. So how this Ferranti effect is coming out from this? Because of this capacitance existence. So whatever the current IC plays a predominant role while developing these type of Ferranti effect. So that's why we can call it as a charging current effect also. I hope it's clear, right? So how we can neglect means you have to minimize this capacitance. So with the help of shunt compensation, right? So always the current that can be flows from the higher potential to lower potential value. Right, always current flows from higher potential to lower potential, right? But here your sending end current is directly flows to the receiving end, right? Now your receiving end voltage is very high, so that means you will see here. So always the current flow from higher potential to lower potential, right? So if this is transmission line, sending end, receiving end. So you are transferring the power from sending end to receiving end. Now here what happened, according to the Ferranti effect, your receiving end greater than the sending end. So that means how the power will flows from receiving end to sending end. So this we can call it as a reactive power. We'll discuss, right? So this we can call it as a reactive power, that we can call it as a negative power. So in order to remove this effect, so we need to reduce the reactive power. So how you can reduce the reactive power? With the help of compensation techniques. Right, in the next SHEM, I think you will get all the compensation techniques, how you can reduce the reactive power concept and all these things, right? So this is about Ferranti effect. This is about a Ferranti effect, how we discussed about mathematical representation and phasor diagrammatical representation and all these things. Thank you very much. In the next session, we will start another effect, very important effect that we can call it as a corona. Right? So that is very important. So I hope each and every student are following my videos. Definitely you'll have a at least brief idea. So what is a skin effect? What is a proximity effect? What is a Ferranti effect? What is a corona? Just brief idea is enough. With the help of these throughout the lectures, I will be a very happiest person if you got a brief information regarding all the effects, how these effects are created in a transmission system. That's enough for me, right? Thank you very much.